Hello everyone. So this is a question from JEE Mains 2026 28 Jan evening. Identify the correct statements. Okay, so they have given us few statements. The presence of NO2 group in benzene ring. Okay. So the presence of NO2 group in benzene ring. Okay. Um, Activates the ring towards electrophilic substitutions. Deactivates the ring towards electrophilic substitutions, activates the ring towards nucleophilic substitutions, and deactivates the ring towards nucleophilic substitutions. Okay, so this involves the chapters like hydrocarbons and haloalkanes and haloarenes. Okay, so the prerequisite to solve such kind of questions is that obviously we all know what is electrophilic substitution reactions, where one electrophile comes, takes the place of another electrophile, and one electrophile goes out. It replaces another electrophile. Same thing happens in a nucleophilic substitution, where one nucleophile comes and another nucleophile goes out. Okay, and we also should know what is the meaning of activation and deactivation. Activation means when something becomes more reactive. Deactivation means when something becomes less reactive. Okay, cool. So also we should know few things about NO2, that NO2 is a meta directing group. So it is a meta directing group, and it is also a electron withdrawing group. Electron withdrawing group. So these two sentences are, if someone is electron withdrawing, that is, it will be a meta directing group. Okay, and how do I know that NO2 is a electron withdrawing group? To know that, so there is an important statement, that is, all the electron withdrawing groups will have an atom directly attached to benzene. Okay, so I will write this down. All electron withdrawing groups will have an atom directly attached to benzene, okay, directly attached to benzene, and having one more electronegative atom linked to it by a multiple bond. Okay, so all the electron withdrawing groups will have an atom which is directly attached to benzene, and that atom will be linked to, it will have one more electronegative atom linked to it by a multiple bond. Okay, for example, in the case of NO2, so let us draw the structure with NO2 attached. So I hope we know that there is one double bond and there is one single bond, and there are formal charges here. Okay, so obviously there are 2 electrons here, 3 4 5 6 7 8, and 4 electrons here, 5 6 7 8, and 4 5 6 nitrogen octet complete. Okay, but there are charges. Okay, there are charges. So let us say this is O1, let us say this is O2. So how to calculate the formal charge in O1? So it will be 6 minus number of electrons involved in bonding. So 1 electron is involved in bonding, so 6 minus 1, and number of electrons present as lone pairs, 2 3 4 5 6 is 6. And what is this 6? This 6 is the valence electron of oxygen. So therefore the charge here will be minus, and the charge on this nitrogen will be, nitrogen valence electrons are 5. Number of electrons involved in bonding, 1 here, and 1 2 here, 3 here, and 4 here. 5 minus 4, and there are no lone pairs. As you can see, there are no lone pairs. Okay, so therefore it is going to be 1 plus 1. So nitrogen has got a plus charge. And O2, let us calculate the formal charge on O2. So now valence electrons are 6. How many electrons are involved in bonding? 1 electron here, 2 electron here. So 5 6 minus 2 minus how many of them are lone pairs? 2 and 3 4. So therefore it is 0. So therefore the charges are negative charge on O1 and positive charge on N. Okay, cool. So now, as you can see, in all the electron withdrawing groups, it will have an atom directly attached to benzene. So in this case, nitrogen, which is directly attached to benzene, having one more electronegative atom linked to it by a multiple bond. See, can you see two nitrogen, which is directly attached to the benzene ring. There is another electronegative oxygen which is linked to it by a multiple bond. Whenever this happens, it is an electron withdrawing group. Okay. Now, because of the presence of this more electronegative atom, it pulls the electrons of multiple bond towards itself. This oxygen is more electronegative, so it pulls these pi electrons towards itself, due to which these electrons are withdrawn from the benzene ring, decreasing the electron density. Okay, so what happens is, if we draw the resonance structure, that is oxygen pulling those electrons towards itself, and because of that these electrons are pulled by N. So the resonance structure shows something like this: double bond N, single bond O, single bond O, 1 2 3 4 5 6, 1 2 3 4 5 6, negative charge, and there is a positive charge here. And a positive charge here also. Yeah. So as you can see, since this is a more electronegative atom which is attached to an atom directly linked to benzene through a multiple bond, so this pulls electron towards itself, because of which nitrogen pulls the electrons from the benzene ring, right? And hence, can you see overall there is decrease in the electron density in the benzene ring, right? Because of the presence of NO2. So that's why it is known as an electron withdrawing group. Okay, so now if we compare a normal benzene ring, and if we compare benzene with NO2, in normal benzene there is no such electron withdrawing groups, right? So therefore, let us say an electrophile wants to do a substitution reaction with this benzene ring. Let us say that took us 10 minutes, for example. And let us say that now the same electrophile wants to attack our benzene ring with NO2. Since there is a decrease in electron density, this electrophile to do electrophilic substitution, it will take more time. Let us say 15 minutes. This is what is known as deactivation. Yeah, deactivating the ring towards electrophilic substitution. It will take more time now because of the lack of electrons, due to the effect of electron withdrawing group like NO2. So therefore we can say that electron withdrawing groups deactivates ring towards electrophilic substitution. Okay, so yeah, so and let us look at it does not activate. So A is not a correct statement, B is a correct statement. Okay, it deactivates the ring towards electrophilic substitution. Okay, now we have to think with respect to nucleophilic substitution. What happens in a nucleophilic substitution? So for that I have some data. If we have chlorobenzene, and if we react that chlorobenzene with NaOH to convert it into phenol, that is, can you see there is a nucleophilic substitution happening, because Cl minus goes out and OH minus takes its place. So it's a nucleophilic substitution. So for this, the reaction conditions are 623 Kelvin and 300 atmosphere. If we have Cl, and if we have NO2 in the para position, and if we want to do the same substitution to get OH instead of Cl and NO2 in the para position, the conditions are 443 Kelvin. Can you see it has become less drastic now? Okay, cool. Now if we have Cl, NO2 and NO2 in the benzene ring in ortho and para position. Again, I'm taking NaOH. So obviously Cl will be replaced by OH, NO2 and NO2. So now the conditions required is 368 Kelvin, and ultimately if we have benzene ring, if we have Cl and NO2 in all the ortho and para position, no need of even NaOH also, just water at temperature 323 Kelvin. So the substitution is going to happen. Cl will be replaced by OH, NO2, NO2 and NO2, right? So can you see that these are examples of nucleophilic substitution? And because earlier the conditions required was 623 Kelvin and 300 atmosphere, the moment we started adding NO2 in ortho and para positions, can you see the conditions are becoming less drastic, right? So we can say that it is activating the ring towards, it activates the ring, activates it towards nucleophilic substitution. Or you can say it is making it more reactive towards nucleophilic substitution, because in the absence of NO2, the conditions were very harsh. But the moment one NO2 group is introduced in the para position, you can see the conditions became less drastic. So it is activating it towards, or making it more reactive towards nucleophilic substitution. So therefore, C is correct. Activates the ring towards nucleophilic substitution. Now, what is the reason behind it? So let's discuss about the reason. Okay. Now, whenever we have electron withdrawing group, NO2 is an electron withdrawing group at ortho and para position. Okay, at ortho and para position, and I'm talking about nucleophilic substitution. So whenever we have electron withdrawing group at para or ortho positions with respect to the halogen, so this is with respect to the halogen. With respect to chlorine, if you have electron withdrawing group at ortho and para position, it activates the halogen towards nucleophilic substitution. So what is the reason? The reason is, so we can write it down, that electron withdrawing group at ortho and para position with respect to halogen activates halogen towards nucleophilic substitution. Okay, this is the point. And the reason is, electron withdrawing group at ortho and para position, whenever they are present at ortho and para position, they withdraws electron from the benzene ring. Obviously their job is to withdraw electron from the benzene ring. They withdraw electron from the benzene ring. Therefore it decreases the electron density from the benzene ring, because they are withdrawing, so they are taking away these electrons. Hence it facilitates the attack of nucleophile, because since the electron density has reduced in the benzene ring, the nucleophile can now attack, because nucleophile has negative charge, right? So it can attack the halogen, and the carbon ion thus formed is stabilized by resonance. Okay, so we'll see. So we'll see which carbon ion we are talking about. So we should write it down that these guys withdraw electron from the ring and also stabilizes the carbon ion. Okay, so we'll see which carbon ion we are talking about. Okay, so let us see some resonance diagrams. So let us say we have chlorine and we have NO2 plus charge and minus charge, right? And this is our para chloronitrobenzene, right? So let's say OH minus is going to attack. So what will happen? OH minus will attack here on this carbon, and this electron pair will shift to this carbon. So we'll get chlorine will get OH, will get a negative charge there, electron pair here, and N double bond O, single bond O minus, right? So this is, so can you see, because of the attack of OH minus, we have created a carbon ion. What are carbon ions? You know, having negative charge on a carbon atom. So this is the carbon ion I'm talking about. So this group stabilizes this carbon ion. We'll see how. Okay, so now what will happen, you can see these electron pairs will become double bond, and this can become a negative charge here. Okay, so the next resonance structure will be Cl OH double bond negative charge, N double bond O, single bond O minus, and plus, and this, right? And the next step will be these electron pairs, they became a pi bond here, and these pi bond became a lone pair there. So the next electron, the resonance structure will be Cl OH double bond here, N O minus and O minus, right? So can you see this NO2 group pulled electrons out from the ring? Now because it is pulling electrons out from the ring, it decreases the electron density here, and therefore facilitates the attack of a nucleophile, because nucleophile is negatively charged. It does not want much electrons in the ring, right? Cool. Now the next resonance diagram will be, this guy will go back, and this guy will become a electron pair, a pi bond here. So we'll be getting Cl OH, and also this pair will shift here, right? So we'll get a lone pair here, negative charge. This will shift here, and this will shift here. Okay, so a pi bond there, yeah, and nitrogen double bond O plus charge, single bond O minus, right? So can you see the carbon ion that we formed initially? So can you see it is resonance stabilized. This is resonance stabilized, right? So because of electron withdrawing groups, there is resonance stabilization, and hence it helps in stabilizing the carbon ion, and it therefore facilitates it towards the nucleophilic attack. Okay, and ultimately what will happen, this Cl minus will go away because it's a nucleophilic substitution reaction, and this will come and form a lone pair there, and ultimately we will get OH electron, N double bond O, single bond O minus, and plus. This is what we are going to get. So p nitrophenol is the product, right? So this is an example of, you know, when NO2 is present at para position. Similarly, we can draw, you know, resonance structures when NO2 is present at ortho position, and we can observe the same thing, that because of the presence of this NO2, it withdraws electron out from the system, and hence you know, facilitates OH minus can easily attack, and you know, so it makes it easy for the nucleophilic substitution to happen because of the presence of NO2, which is electron withdrawing. So this is the reason why at ortho and para positions, electron withdrawing groups you know, facilitates, or you know, helps or makes it easy for the nucleophilic substitution reaction to happen. Okay, so therefore these are the two correct statements, that it deactivates the ring towards electrophilic substitution because NO2 is electron withdrawing, it withdraws electron, reduces the electron density, electrophile wants more electron, does not get those, that's why it, you know, deactivates towards the electrophilic substitution. For nucleophilic substitution, a nucleophile is going to attack, right? Nucleophile wants less electron density because it likes positive charges. Because of the presence of electron withdrawing group like NO2, it withdraws the electron out, decreases the electron density, and activates it towards the nucleophilic substitution. Okay, so B and C are correct statements. Okay, thank you.